Hello and welcome to a presentation on neoclassical physics. My name is Bharat. I did my BE in computer engineering from KREC Surathkal. I got my master's from IISc in the field of atmospheric and oceanic sciences. Then I spent a long time studying Indian monsoon and earth system modeling as a PhD student. During my studies on monsoon, I realized that more than the computational difficulties, much of the underlying physics in climate science is itself erroneous, and that causes the predictions to go wrong. Further, over more than a decade, I discovered some serious errors with basic physics. Einstein, Maxwell, Bohr, Boltzmann, almost everyone has got some key aspects wrong. One such error is the Newtonian method of framing force balance equations governing the motion. Newton's method is not universal. They are merely a small subset of all energy conserving processes. Since Feb 2020, I teamed up with Amit, founder WinProtect, to start Neophysics, an R&D lab. This lab is going to disseminate the new physics first and then collaborate with like minded non-conformist hackers and crackers to create amazing new technologies possible from this new science. Now let us move on to discuss the work of Kepler. Through data analysis, Kepler proposed that the planetary orbits are elliptical. The sun is stationary at one of the focus. We choose this as the origin of our coordinate system. R and theta define the position vector of the planet. Let us now look at the formal statements of Kepler's laws. You can pause and stare at this slide to understand the characteristics of an ellipse. Among all the analysis presented by Kepler in his books The New Astronomy and Harmonies of the World, three statements stand out and they have been recognized as laws. First law states that the planetary orbits are elliptical, as seen in the previous slide. Equation 1 shows the parametric equation of an ellipse. This other form is used in some cases. Second law, in its modern form, is a statement about the angular momentum conservation. The constant A is also the area covered by the planet per unit time. Third law connects the length of the semi-major axis with the period of revolution. Newton not only connected the constant occurring in the third law to the mass of the sun, but also derived its relationship with the constants occurring in the first two laws of Kepler. The genius of Newton lay in recognizing the fact that this same celestial mathematics is applicable to terrestrial motions as well. This terrestrial celestial connection leads to the concept of gravity, that every object attracts every other object as stated in the gravitational force law. Starting from Kepler's laws, we can derive both Newton's law of gravity and energy conservation equation. Then we shall explore the relationship between those equations. Let us now consider the time derivative of Kepler's first law. By applying the first two laws, we get dr by dt equals a by r naught epsilon sine theta. Using the alternate form of equation 1, we can eliminate theta and get this expression. We will use it later. For now, we shall proceed to find the second time derivative of r. We get d square r by dt square equals a by r naught epsilon cos theta d theta by dt. Again, using first and second laws, we can eliminate theta and get this expression. Since a and r naught are constants, a square by r naught will also be a constant. We shall call it b. By solving the differential equations like equation 4 or equation 5, it is easy to show that b is the same constant that occurs in Kepler's third law. For now, we are interested in deriving Newton's law of gravity, so we further elaborate on second derivative that we found in equation 5. Using Kepler's second law, we can replace a square by r cube by r d theta by dt square. This is equation 6. Then we can consider the first time derivative of Kepler's second law. Since a is constant, dA by dt is 0, so the derivative of the RHS will also be 0. Taking r common out, we get equation 7. Equation 6 and 7 can be elegantly combined together into one vector equation. Let r be the position vector, then we can express the second time derivative of position vector as this. The term in the square bracket with r cap is the LHS of equation 6. The term in the square bracket with q cap is the LHS of equation 7. Using them, we can rewrite acceleration as this. Gm by r square gives the magnitude of acceleration. From Newton's second law of motion, we know that force is defined as mass into acceleration. When we combine this definition of force with the acceleration term derived in equation 8, we get Newton's law of gravity. Note that the inverse square dependence of uh, acceleration is a result of Kepler's laws itself. Newton introduced the idea that there exist force laws which govern the motion of objects. Newton's law of gravity in that form is true only for unconstrained motions. In constrained motion, for example along an inclined plane or along a brachistochrone, we need to consider only that component of gravitational force which affects the acceleration of the object under consideration. Finding that component is not trivial and it is not part of Newton's standard three laws or the laws of gravity. In fact, finding the force component on an object in a brachistochrone trajectory using free body diagrams is impossible. Other formulation to solve such problems using the Lagrangian method depends on using the kinetic energy and potential energy terms in a rather complicated way. In fact, energy conservation equation offers the easiest method. Let us now look at the derivation of energy conservation equation directly from Kepler's laws. That is, without relying on a definition of energy based on pre-existing concept of force. We can as well think that energy is the primary quantity and force is derived from it, rather than assuming force as primary and energy is secondary as in the Newtonian paradigm. Taking square of the theta eliminated version of dr by dt equation from equation 4 on page 3, we get equation 12. In equation 12, this is a variable. These terms are also variables, but the sum of three variables is a constant quantity. By using B equals gm in equation 12, we get equation 13, which is the equation of total energy per unit mass. If we multiply equation 13 with small m, that is the mass of the planet, we get the energy equation. As such, we get an equation with negative energy, but we can use it as it is in many problems. Or we can also add a constant factor g mm by big R on both sides of the equation to, to make net energy positive. Here, big R is the lowest possible distance between the two objects, and small r is always greater than or equal to the big R. This form will be useful in some problems. The net kinetic energy in vector notation is shown here. The time derivative of the potential energy is as shown here. It can be expressed as a dot product between force and velocity. Here, force is defined according to Newton's law of gravity and not according to Newton's second law of motion. The laws specified by Kepler correspond to what is now known as one-body approximation. Newton tried generalizing it to two or more bodies and succeeded partially. One-body approximation has been found to be good when one of the interacting objects is massive compared to the other, because we can assume the massive object is practically at rest and the kinetic energy of the smaller object represents the entire kinetic energy of the system. Potential energy is a shared term and belongs to both the objects. Thus, the net energy of the two-body system can be written in one-body approximation form as shown here. Now let us take the first time derivative of total energy. Then we get this dot product on RHS. When energy is conserved, dE by dt is 0. Therefore, the dot product must also be 0. Hence, there arises two conditions under which the dot product can become 0. 1. When one of the dot product term is 0. Velocity cannot be 0 at all velocity cannot be 0 at all times if the object is moving. The Newtonian force balance term in the brackets can become 0. This is the Newtonian method, which equates mass into acceleration with gravitational force defined using force law. If this term is 0, then naturally dE by dt will also be 0. However, in case of motion along inclined planes or brachistochrones, Newtonian equation is not valid, yet the dot product remains 0 and energy is conserved. Because the non-zero residual Newtonian force balance term in the square bracket remains perpendicular to the velocity vector at all times. Thus, Newton's equation is only a small subset of all energy conserving processes. Whenever Newton's equation is valid, energy is necessarily conserved, but whenever energy is conserved, it is not necessary that Newton's equation is valid. Let us now look at what equation 19 becomes in case of n-body interaction. Suppose these two lines represent the coordinate system and their point of interaction is the origin. We have numbered each mass 1, 2, 3, etc. up to n. The ith mass is labeled mi and the jth mass is labeled mj. The position vector of mi is vector ri and the position vector of mj is rj. Using Newton's law of gravity, we can find pairwise force terms F subscript ij. The net force on mi is Fi. It is the summation of all individual pairwise force values on mi due to every other n-1 masses in the system. Equation 10 is how we frame equations of motion in Newton's method. The acceleration of mass is determined by vector summation of individual pairwise forces generated according to Newton's law of gravity. So if there are n interacting bodies, we get a set of n simultaneous ordinary differential equations. Now let us look at the total energy equation of the n-body system. The pairwise potential energy is as described by P subscript ij. d by dt of Pij has the same dot product form as in equation 14 on page 7. The total energy of the system is the summation of all the kinetic energy terms of the n objects and the summation of all n into n minus 1 by 2 pairs of potential energy terms as shown in equation 16. Equation 16 can also be written as equation 20. With a bit of calculation, we can see that the time derivative of the total energy equation of the n-body system turns out to be a summation of the dot products. Individual dot product terms are similar to equation 18 on page 8. When energy is conserved, d by dt is 0, so the summation of dot products also becomes 0, as we can see. The Newtonian method is a very tiny subset of all possible processes where energy is conserved. There are many more possibilities. The energy-based method offers an easier and comprehensive way to understand and analyze some complicated problems such as the nodal and apsidal precision of orbits. In case of three-body problem, we can note that the force-based method gives few sporadic stable solutions and most often ends up in a chaotic situation. But energy-based analysis provides a proper set of stable solutions without any chaos. The non-universal character of the force balance equation in comparison to the energy conservation equation has deeper implications in all places where force laws and force balance equations have been used. That includes electrodynamics, fluid mechanics, magnetism, thermodynamics, virtually all of physics. Besides, when the energy is not conserved, some power is being extracted or delivered when the Newtonian formulation does not adequately describe the phenomena as described by equation 20 and the power equation or d by dt equation associated with equation 20 on page 12. Much of the interesting n-body configurations actually happen at lab scale in electrodynamics. We shall explore them in future presentations. Thank you and visit our page neophysics.com.